Welcome back, everybody. Dr. Schoffers here, checking in with you as we are discussing Chapter 23. Chapter 23 is concerned with organometallic compounds. We'll only cover a couple of the sections that are introduced in this chapter. I'd like to mention that for virtually every organic functional group that we have learned about, there is an interaction with a metal that can influence the reactivity. We're only scratching the surface here, and I'll start out by summarizing some of the objectives and discussion points. So in Chapter 23, we are focused on the first four sections. We're talking about the general properties of organometallic compounds. We'll then focus on organolithium compounds, as well as organomagnesium compounds that we know as Grignard reagents. We're also dealing with the Gilman reagent, where we're essentially dealing with cuprates. And then there are organozinc components or compounds that can help us form a three-membered ring, and this is a named reaction, the Simmons-Smith reaction. So all the remaining sections in this chapter are omitted. Here are some of the selected learning outcomes. Describe the structural features. We need to understand the polarity, the dynamics that now shape what is a nucleophile or an electrophile. We discussed the preparation and properties of the organolithium and organomagnesium compounds, as well as the Gilman reagents. And as a named reaction, it's a mouthful, we can make some very powerful new bonds in the Corey-Posner Whiteside's house coupling reaction. And it is a coupling reaction, so that's a new kind of way of thinking how we are forming these bonds. And then we're also discussing the Simmons-Smith reaction, which is a cyclopropionation reaction, meaning that you are forming a three-membered ring. And this relies on the connection of carbon with zinc. Before moving on, you may want to pause here and review in detail which sections will be important as they are being applied in here. So that ranges from Chapter 1 to Chapter 12, where we learned the reactions, various Grignard reagents for the preparation of alcohols. We need to understand the stereochemistry of alkenes, because we have some specificity that we observe in the transformations, and also carbon nucleophiles as discussed in Chapter 19. The next slide goes over some of the basic properties of organometallic compounds. Recall that as we are comparing the carbon-lithium bond, the carbon-magnesium bond, and the carbon-copper bond, here now shown in the form of a cuprate, which is a salt, we can now actually look at the placement in the periodic table and understand one of the foundational pillars, which is electronegativity and its consequences. We know that lithium is a main group number 1, so we see it here, and then here we have magnesium, and here is zinc. So we're going from left to right. We have increased electronegativity. That now also affects this bond and how it reacts under various circumstances. On this slide here, basically, as we're looking at the properties of organometallic compounds, we want to recall the differences in reactivity. This was also addressed in Chapter 20. Remember that we had used acid chlorides, so a carboxylic acid derivative in the presence of a Grignard reagent, and we had learned that this is basically a vehicle for generating a very strong nucleophile. So we can think of this as forming a methyl dot minus. So a very potent nucleophile that's going to attack the carbonyl group, and this can happen twice. So we're introducing actually two of the same substituents to form a tertiary alcohol. When we compared the same starting material, a carboxylic acid chloride, reacting with an organocopper reagent, so here's your Gilman reagent, we wanted to think about also in terms of transferring a methyl group, but here it only transfers it once, and the carbonyl group is retained. As we're looking at the reactivity, Grignard reagents are far more reactive because the carbon itself is going to be a much stronger nucleophile compared to the more moderately reactive Gilman reagent, where we have copper here. And we will discuss in the fourth section the organozinc components. All right, so now that we've compared Grignard with cuprates and understand that reactivity varies, let's dig in some more. We also had looked at Michael reaction. Michael reaction is a conjugate addition reaction, and basically what we're dealing with is a 1, 2, 3, 4 system, and that the Gilman reagent will actually prefer to attack in the 4 position where the new methyl group is introduced. Remember that you're only transferring 1 methyl group, so this is the vehicle for transferring 1 methyl group, and it will be in the 4 position. Remember that we number it 1, 2, 3, 4. And here's your methyl group that has been introduced in the structure, and the double bond has disappeared. If we were to use a Grignard reagent in here, we would get a 1,2 addition as previously discussed. So organolithium and organomagnesium compounds, when we compare these two, they have a lot of similarities. They possess a high degree of ionic character, and therefore we can see similar reactivity. So again, we can think of organolithium reagents as an ionic bond. This is a vehicle for delivering a very strong nucleophile R dot dot minus. Depending on, we can actually swap this out with other groups. The same can be said about the Grignard reagents. So again, we think about them as strong nucleophiles R dot dot minus. So, some more information. Let's first dig deep in the second section on organolithium reagents. So they can be obtained from alkyl halides, as we see here, Rx. These can be chlorides, bromides, iodine, typically in a nonpolar solvent like hexane. Since a protic source will actually eliminate elemental lithium. What you see here, we typically have excess of lithium, 2 equivalents. 1 equivalent replaces the position of the halide, so we get an R lithium bond, and then there's a salt that as a side product now would be the lithium halide, so lithium chloride, lithium bromide, lithium iodide. What is very encouraging about this is that this works best with primary halides. As you see here, this carbon has only 1 rest group attached, and we have the polarized carbon-chlorine bond. Now this is being replaced with the lithium, and we get the salt as a side product. What's exciting to see is that we can use sp2 hybridized carbons as well, such as in this aromatic compound, this phenyl bromide or bromobenzene, as well as vinyl groups. So as you see here, this is also sp2 hybridized. We've never been able to do a de facto substitution, and this is actually the mechanism for these transformations is beyond the scope of this class. But we should remember that the halide basically is being replaced on sp3 and sp2 carbon centers to now have these very reactive intermediates, and then to look at their further transformations. So organolithium compounds are obtained from alkyl halides, best in nonpolar solvent, as we said, and now they can act as really strong nucleophiles. Here I have 2 examples given, and you may want to pause here, jot down the structures, and then think about what will happen next. I'll give you a couple of pointers. Again, basically we're swapping this out. We don't care about the salt that is a side product. Now this is a very strong nucleophile. How would this react with formaldehyde? Formaldehyde is the simplest carbonyl compound that exists. It's an aldehyde, and it has 2 hydrogens attached. And of course we know that the carbon-oxygen bond is highly polarized, so you're going to do a nucleophilic addition followed by a tetrahedral intermediate. Make sure you follow the charges, and you can therefore now form an alcohol group in here. Similarly here, this is now sp2 hybridized, but we have the same thing. Now all of this would be your nucleophile that is attacking, after the chlorine has been replaced with the lithium group, it will be attacking this carbonyl group. And I recommend that you actually form that you actually draw a chair conformation of this reaction here, because this will actually have selectivity in terms of where it approaches. So make sure you draw out a chair, and I encourage you to use your models to see now the sterics, and one of the carbonyl faces will be favored over the other. Recall that the synthesis of organomagnesium compounds is very similar. We start out with a halide. So these are our Grignard reagents. We basically get an insertion into the RX bond. So we get RMGX. But remember, this is a very powerful nucleophile, R dot dot minus, that is generating in these reactions. And the interesting thing here as well is that we can use primary halides, so sp3 hybridized as well as sp2 hybridized as an aromatic or in a vinyl compound, and we have the variation between chlorine, bromine, and iodine. We also want to pay attention to the fact that we typically use an ether solvent, so diethyl ether is shown here, or we can utilize THF, tetrahydrofuran. That is a cyclic ether that you should still remember from Orgo 1 and from previous discussions. So there's no protic source which would actually quench the organomagnesium compound, and here you see some chelation activity. This acts as a Lewis base. Two molecules can actually chelate the magnesium, which is delta positive, but ultimately we have also then the delta negative here on the halide, and then the delta negative here. Thus we are looking at these as a source of R dot dot minus. Looking on, so we need to also understand that these organolithium and organomagnesium compounds, because they deliver very powerful R minus, that they can not only be strong nucleophiles, as we want them to react most of the time, but that they're also strong bases. So we have to make sure we keep away protic substances, because they will react with protic substances. So anything that will have an active H. Here you see a reaction where a Grignard reagent is being quenched by a water molecule. Here now this is picking up a proton, now forming a carbon-hydrogen bond that is very, very strong, and we get a salt side product. We want to be aware of this aspect, because if we are choosing a substrate that has a protic source, such as an alcohol in this molecule here, we cannot use magnesium. We actually would have to protect the OH group first, replace the hydrogen temporarily with something else, and then later on deprotect it if we wanted to generate a nucleophilic component of this carbon halide bond. So this is something that's very important for us to differentiate as we design syntheses and have more than one functional group present. Here is a review of the various magnesium compounds, how we had applied them. We had seen the addition of, again, we're thinking here about our R dot dot minus as a strong nucleophile. In chapter 12 as well as in chapter 20, we discussed the reactions of carbonyl compounds. We can form alcohols. We also can utilize this very strong nucleophile to open up an epoxide, especially with a symmetrical epoxide. It doesn't matter which side is opened up, and we are integrating two more carbons in the structure. So epoxide is used to elongate the chain by two carbons, and this was discussed in chapter 13. We can also see reactions with CO2 that then lead to carboxylic acids. We have a couple more review topics here. We have seen that Grignard reagents, so this R dot dot minus, can react with esters and now form tertiary alcohols with the two same R groups, rest groups. And we have also seen how R dot dot minus can react with nitriles, and the reaction begins by actually attacking this delta positive carbon, and the mechanism was discussed previously. You may want to look at chapter 20 again, and then again I recommend that you practice a lot of this material so you can understand the gist of these conversions. So, thinking about practice, here I've actually pulled up a couple of transformations. So just what we had looked at in the previous slides. Think about the reactivity. Here you have an ester group, here you have an epoxide. You know that D stands for an R dot dot minus, and I encourage you to jot out the products to understand the overall conformation.